All right, in this video, we want to solve this inequality over here, and we want to get the solutions for x. So we basically want to find where 1 over 2x is greater than 2 sine pi over 4 x. Now, this is a linear equation, and this is a trigonometric equation. And in this case, there's no algebraic way to solve this. The question asks us to first solve this graphically. So I'm just going to do it freehand over here, which won't be as accurate if you're doing it on graph paper, but you should get approximately the same solution. Let's start by sketching 1 over 2x. 1 over 2x is simply a graph, a linear equation with a positive slope of 1 over 2. So it passes through the origin because there's no y-intercept in the equation there. And then the slope is 1 over 2. So as I go towards the right and towards the left, my slope is 1 over 2. So for example, over here, when x is 1, y is 0.5. When x is 2, the point here has a y value of 1. And then when I get all the way till 4, I skip 3, but 3 is just 1.5. 4 will have a height of 2, and so on and so forth. 6 will have a height of 3. Basically, we just have a slope of 1 over 2, and the same values will repeat on the negative side over here. So exact same points with negative values. For 2 sine pi over 4x, my amplitude is 2. My k value is pi over 4, which means that my period is 2 pi divided by pi over 4, which is 8. My equation of axis is just y equals to 0 because there's no c value at the end, and there's no phase shift over here. There's no reflections. So let's draw our sine wave. Sine wave, I know, starts on the origin. It goes up to the maximum. So since we have a period of 8, if I take my period and divide it by 4, because sine waves and cosine waves are always split into 4, I'll get a difference of 2. That's going to be the next key point for all my x values for my sine function. So for example, I start here. My next key point is going to be at 2 and 2, the maximum. And the next key point is going to be at 0 and 4. And I'll go down to negative 2 and 6. And then finally, the first period will end at positive 2 and 8. Oh, wait. You know what? Looks like I missed something here. 0, 2, 4, 6. Oh, wait, it ends here, not at the top. I don't know why I put it at the top. Cosine wave ends at the top. 8 ends on the axis here. So that's my sine wave. I can start drawing it out. And basically, the negative side will reflect this exact same thing. So I'll draw out the negative side as well. And this is just negative 8 and negative 4. And this in the middle, the minimum is negative 2. If you draw on graph paper, it should look approximately the same. Now we want to find where the linear equation is greater than the sine equation. So where's the straight line above the trig line? In order to do that, we need to find all the points of intersection of these two functions. So there's the first point of intersection here, the second one at the origin, and the third one over here. So if I look at this and I look over here, the line is below the sine equation, so this is no good. Then I reach this point here, and the line is now above the trig equation. So my first solution to this question is this range over here. Well, what are the x values of the range? We can approximate this as -3, and we know that for sure is 0. So my first solution to this inequality, we're going to use round brackets because there's no equal over there, is from -3 till 0. That's where the line is above the trig wave. Then when we continue here, the line is below the trig wave, which means that this is no good over here. This inequality is untrue. But once we reach this point here, the line is above the trig wave all the way till infinity. So this is in union with +3 till infinity. So there are two places where the line is above the trig function between -3 and 0 and above -3 or from 3 till positive infinity. Now this is just an approximate solution because when graphing, these are almost always approximate solutions. The next part of the question tells us to find a more accurate solution, and we're going to be using guess and check because that's the only more accurate way to find it. So in order to find a more accurate solution, we need to go into a bit of decimals. Okay, so we need to find this point of intersection right over here and this point of intersection right over here a bit more accurately. We know this for sure is 0, 0 because all three of these, or all two of these functions, both these functions pass through the origin. So we just need to find these 2 points a bit more accurately. So in order to do that, I'll sub in a point really, really close. I'll pick this one here. Okay, I'll do this one over here. I'll test with this point first. So I'm going to try 2.9. I'm going to test 2.9 and I'm going to test 3.1. I'm going to put it in these equations to see what I get. So if I put 2.1 in this equation, I'll do it in my calculator. 1/2 times 2.1 is 1.05. And then if I put it in this side of the equation, make sure your calculator is in radian mode. And remember, we want both sides to be exactly the same because that's what happens at the intersection points. So if I do 2 sine pi/4 times 2.9, I get 1. Oh, I have a slight mistake here in my calculation for the first one. This is not 1.05, this is 1.45. Sorry, slight mistake. And for this one, I get 1.52. So these are close, but they're not exactly equal to each other. Let me test 3.1 and see what happens with 3.1. So if I put 3.1 in this equation, I'll get 1.55. And if I put 3.1 in the second equation, I will get 1.3 basically. So if I compare these two answers, I know that this one is much closer to being my solution. So because these two values are much closer together compared to these two values, these two are too far away. So I know that 2.9 is definitely more accurate than 3.1, which means that my solution is somewhere between 2.9 and 3. So the next value I want to test is something in between 2.9 and 3, because I know my solution is most probably between one of these two. It's possible it could be slightly less than 2.9 as well. It could be 2.8, but you always want to test between numbers to see whether you're getting closer or further. So I'll test 2.95 next. If I put 2.95 in the first equation, I get 1.475. And if I put it in the second equation, I get 1.469. So now I'm extremely close, much closer than these 2 points, which means my answer is definitely really, really close to 2.95. So potentially even 2.94 or 2.96, but somewhere really close to 2.95 because this gap is even closer. And you can tell that the numbers are getting closer to each other compared to these. So I'll test something slightly smaller like 2.94, and if this gets further, then I'll test 2.96. So if I put 2.94 in my equation, I get, for the second one, I get 1.479. And for the first one, I get 1.47. So as you can tell, this is also extremely close. These are extremely close, which means my solution is basically 2.94 or 2.95 or somewhere in the middle of these two. If you want to go even more accurate and go to 3 decimal places, you can test something directly in the middle of these two. For example, you can test 2.945. If I sub in 2.945 in the first equation, I get 1.4725, and if I sub it in the second equation, I get 1.474. So these are even closer. And I think this is honestly close enough. I mean, you could technically try and find the exact value by changing this third decimal place here, going up or down by a couple of units. Its answer is probably like, if it's rounded to 3 decimal places, could be 2.946, 2.944, 2.947, things like that. You can actually test out each values. And if you want, I'll quickly test all of these in my calculator to try and find the accurate solution, but I won't write them down on paper because that's going to take too much time. So if I put 2.944, I get pretty much the same exact answer. And if I test 2.946, it's also pretty much, oh, it's identical. So if you put 2.946, again, I don't think you need to go this far. Ending on 2.945 is pretty much going to give you full marks for sure. But the exact same value is from 2.946, which gives me 1.4729 is greater than 1.4729. So I know that this is the exact value. I mean, I don't even have to round because these are like the exact same number, which it ends up as somehow being the exact same number with the sinusoid in a linear equation. So we know that instead of writing our final answer like this, we can write it from negative 2.946 to 0 union positive 2.946 to infinity. Because these graphs are both even, these 2 points will have the exact same value, just one positive and one negative. And now using guess and check, we found the exact value of the solution.